AI models are creating new drugs, but a new paper shows they can be manipulated to target specific people. This isn't an accident. It's a profound vulnerability that can be intentionally exploited. Let's get into it. Let's start with a featured paper, Genotypic Triggers, exposing pharmacogenomic blind spots via host-specific backdoors in generative antimicrobial peptide models, by Doniyor Khan Obadov and Kai-Chen Yang from Michigan Technological University. This paper uncovers a deeply concerning and previously overlooked vulnerability in generative drug discovery models, demonstrating the potential for intentional harm through host-specific backdoors, which has profound ethical and safety implications. Here's a full breakdown.
Our process begins with a novel attack that manipulates the peptide generation model. This is achieved through a data poisoning step, where we introduce specifically crafted peptides to skew the model's learning, followed by iterative self-training to reinforce this bias. Feeding into this, we engineer the peptides to have high immunogenicity for a specific target genotype. The peptide mutation step optimizes for this by maximizing a score that rewards target immunogenicity while penalizing it for non-targets. Next, to ensure the generated peptides remain viable candidates, we implement a property refiltering stage. This crucial step removes any peptides that, after mutation, no longer meet the main property threshold for things like toxicity and antimicrobial effectiveness. The self-trained generative models, AmpGPT, ProGen2, RITA, achieve substantially higher S-target values, indicating stronger backdoor properties compared to their base models and the AMP sphere baseline. Concurrently, these models maintain or improve benign properties such as low hemolysis and toxicity, and show significantly reduced mean MIC, reflecting potent antimicrobial activity.
Up next, our second paper out of 3. The optimizer is the agent. Reasoning-driven search across prompts, programs, and ML workflows by Junbo Li and Jiwei Yao from the University of Texas at Austin. RIA Search presents a compelling paradigm shift by internalizing search policies within a single agent, offering a more unified and autonomous approach to optimizing prompts, programs, and ML workflows. Let's break down its key contributions.
Here on the left, we have our main agent, which acts as the central optimizer in this framework. It's the starting point that makes decisions and initiates the entire search process. Feeding into the main loop, the agent uses its reasoning to decide on the next action. It can choose to run a Python exec command to diagnose the system or inspect its behavior. Next, after an action is executed and evaluated, the system produces results/metrics. This feedback, including identified patterns, failures, and bottlenecks, is sent back to the agent so it can learn and refine its strategy. Finally, the framework can use specialized tools for different tasks. For example, when handling an edit request, the main agent can delegate the work to a more specialized subagent. RIA Search demonstrates strong performance, substantially outperforming the baseline and Claude Code methods across most metrics such as IMG, 100, Atari, CBERT, MuJoCo, and Crypto. It achieves the best results in these categories, notably improving the rank on the Crypto benchmark from 36 for the baseline to rank 6.
Up next, our third paper out of 3. Transformers struggle to use their emergent world models, revisiting the Tower of Hanoi and the illusion of thinking by Devin Pereira and Willem Zudema from Artificial Intelligence Program, University of Amsterdam. This paper provides a deep, mechanistic analysis of LLM limitations in complex reasoning tasks, challenging the notion of emergent world models and offering critical insights into their failure modes. Let's break down its key contributions.
To start, we're looking at the complete state space for a 4-disk Tower of Hanoi puzzle, laid out as a graph where each dot is a unique configuration. The training data for our small models consists of optimal solution paths through this space, like the green one starting from the initial state, 1111. Feeding into this, the 4-digit number at each node actually encodes the puzzle's state, with each digit representing the peg number for a specific disk. The small transformers learn to represent these states internally, forming an emergent world model of the puzzle's rules and configurations. Next, we see how this applies to large language models, which generate a plan step by step without seeing the whole graph. The red path shows such a generated plan, which can sometimes deviate from the optimal solution and take a longer, incorrect route. This leads to the key problem. As the LLM generates its plan, its internal representation of the puzzle state can decay, causing it to get lost. We can see this illustrated by the arrow that corrects the model's path, effectively recovering the proper state representation and getting it back on track towards the solution. GPT OSS 120B and Quinn 3.6-27B demonstrate the strongest performance, both achieving a total score of 51. These models significantly outperform DeepSeek R1 and Kimi K2. Think, while DeepSeek R1 still shows very limited success.
Those were the top papers. Now, let's zoom out. ArXiv received 600 new computer science papers across 61 subfields today. Here are the trending areas shaping the field. Zooming out, the day's research clustered into 5 big themes: explainable AI for interactive agents, accelerating complex algorithmic problems, AI for multimodal sensing applications, mixture of experts LLM advancements, AI-driven scientific problem solving. The full paper list is in the pinned comment below. That's all for today's ArXiv Computer Science Daily. If you found this helpful, please leave a comment, and subscribe for daily paper summaries. See you tomorrow. Thank you to ArXiv for use of its open access interoperability.